Hello and welcome to our 2020 NeurotechX competition submission for Merlin Neurotechnology. Our remote submission this year is a pip installable Python package named Neurol, which we created to help streamline BCI development within Python. As an example of the package in use, we'll be demonstrating a script we created named AlphaLight that configures elements in a smart home environment using the Internet of Things and EEG. We're a team of undergrad students based out of Queen's University in Kingston, Ontario, Canada. My name is Lucas, and I'm the current captain of the team, but there's many more of us working remotely. I'll be providing the inspiration behind and the overview of the project, and other members will continue the discussion on more specific elements of the project. As a cross-discipline undergraduate design team, technical accessibility to the field of neurotechnology has always been one of our priorities. In addition to improving the educational aspects of the club, we wanted to make sure that the learning curve for BCI development was more friendly as well. Our guiding question for the project was this: how do we improve the accessibility for BCI development in Python for programmers and hackers new to neurotechnology? Our proposed solution this year is Neurol.
The process of developing BCI usually follows a similar pattern. First, data is streamed from some source like an EEG headset. Once we have the data, we apply transformations to it depending on our application. This hopefully makes it easier to classify the data, which we can do using statistical or algorithmic methods. Finally, we perform some action in response to the classification output. Neurol, which is our submission for the competition, uses this idea to implement brain-computer interfaces in a modular manner. Neurol handles all processing of the stream of data and makes it easy for programmers to define their BCI's intended behavior by simply passing functions for each part of the pipeline, and that's all applied in real time as new data is coming in. At the core of Neurol's BCI functionality is the generic BCI class. This is our most basic BCI class, and the others are built on top of it. It can be defined and initialized by providing the following functions. First, an optional calibrator, which runs at startup and can provide useful user calibration information to the transformer and classifier. Then we can provide an optional transformer, which transforms the newest buffer of data into the form that's expected by the classifier. We often use this to convert to the frequency domain. Of course, we need a classifier, which decodes the data into some classification of brain states. And finally, we provide an action function, which provides feedback in response to the decoded brain state. Once these functions are defined, we only need a stream of data and the BCI can be run. Neurol is compatible with any LSL stream, which is an industry standard for real-time BCIs and can be used to stream any kind of brain data. Neurol also contains more elaborate BCI classes, which will be useful for more complicated projects. There's FSM BCI, which implements a BCI inspired by the way that finite state machines work. Here, the classification of brain state is not only dependent on the real-time brain signal, but also on the previous brain states. Taking that a step further, we have retentive BCI, which implements a BCI with memory of past brain states so that classification can depend on the history of previous brain states, up to some memory length. And finally, there's AutoML BCI, which builds its own classifier by training a machine learning model in a calibration stage. We'll talk more about AutoML BCI when we demonstrate Neurol in action. To further fast-track BCI development, we also include a range of utility functions and visualization tools in Neurol to make defining the BCI's behavior as easy as possible. For example, there's a band power transformer, which returns the power of each EEG frequency band from theta to gamma. There is band power calibrator, which helps get a baseline of the power of each of these frequency bands. And then there's functions like ensemble transform, which makes it easy to define a sequence of different transforms and packages it all together. Finally, Neurol has some nice visualization functionality to plot real-time streams in the time domain or the frequency domain, or as a colorful spectrogram. Neurol has full documentation and example notebooks, so if you're interested in learning more, please feel free to check it out on our GitHub.
With the overview of Neurol explained, let's take a look at it in action. In only a short period of development time, club members using Neurol were able to create a BCI system to control elements in the smart home environment. The modular approach to development encouraged better creativity and freedom when programming the function in the BCI's action component. We used the Philip Hughes Smart Lightbulbs API to connect to a smart light bulb over the internet. Then, depending on the classification output from the BCI's classifier component, which we use to determine relaxation or concentration, the light color changes from a vibrant green to a deeper blue.
So let's take a step back and take a look at the modular components from Neurol that made up this project. As we mentioned before, there's a sequential list of functions that are defined by the user and passed into the BCI class. First, we have the calibrator. Then we have the transformer. Next is the classifier. Then finally is the action, which takes the decoded state from the classifier. In the first version of AlphaLight, it used the general BCI script and contained the following structure. Calibrate. Use the band power calibrator function to get a baseline value for average alpha wave magnitude for that user. Transformer. Use the band power transformer function on the incoming stream to transform into the frequency domain and provide magnitude outputs for the alpha low and alpha high bands. Classifier. Use the value from the calibrator in a thresholding function to compare to the incoming data from the transformer. If the incoming stream data has a lower alpha wave magnitude than the alpha wave average sampled in the calibrate step, then you consider it more concentrated. Action. Takes the output of either not concentrated or concentrated from the classifier. If it's concentrated, you make the light more blue. If it's less concentrated, you make the light more green. After adding these functions in as parameters to create a BCI class instance, we can execute the run method and pass in the LSL stream object into the line of code. The outcome looks like this.
To further demonstrate Neurol's BCI classes, the user has the option to easily apply machine learning algorithms rather than using a manual thresholding function. This process instead uses the AutoML BCI class and requires just the lines of code shown on screen. If you want to use machine learning with Neurol, you simply pass in a model object with fit and predict methods, specify the epoch length, the number of states, and set a training data recording length. In this class, the build model method replaces the calibration method from before. Neurol handles the data repackaging, labeling, training, testing, and implementation of the machine learning model all automatically. The easy implementation of machine learning techniques in Neurol is something we are especially proud of.
The control of this light occurs fully through the internet using the Philips Hue API. We chose control of this smart device because of the capability for simple visual feedback. However, the modularity of the action function makes it trivial to substitute this action with any other device, whether it uses Internet of Things or not, that has Python API support. At this point in the code, the developer just works with the classification output, so the creativity you can have is endless. For the future of Neurol, we plan to continue to use its framework in Merlin, both as an accessible means of entry for our club's new developers, as well as to provide the structure for more advanced BCIs in the future. The scalable automatic handling of LSL streams is especially important for testing, as the remote schooling this year means that different members of the club may have different Neurotech headsets with themselves at home to test on. Whether you're on a Muse, an OpenBCI board, or any other source that has the ability to send LSL streams, Neurol simplifies that process. Beyond club usage, we hope that Neurol can help reduce the barriers and speed up BCI development for other developers, hackers, and hobbyists in the field of neurotechnology. Thank you so much for watching our submission, and we're all so excited to see the other fantastic projects presented this year. On behalf of Merlin, we'll see you next year.